Hi, this is Mr. Heineman from Evergreen High School. This is for my Algebra 1 classes. This is Standard 1.1, the structure of expressions. So systems of equations are groups of at least two equations that use the same variables. And for our purposes, we will always be using systems that have only two equations and two variables. And those variables will pretty much always be x and y. So if there is a story that accompanies the system, or if there's a story where you have to create a system, then the variables must represent the same things. So that way we know that they're the same variables and they're representing the same things in the story. So that's really all a system of equations is. We're going to start by getting into solutions. So as we found in linear equations, systems of equations have solutions that are points, and in this case they're points that make both of the equations true in the system, which means that systems have only one solution, and on the graph that means it's the intersection of the two lines. So when we look at a system of equations, there's only going to be one point that is a solution, and on the graph that means it's the point of intersection of the two lines, because our equations in our systems will all be linear equations. And so we could graph the lines. The intersection of the two lines is the actual solution to the system. So we should also be able to find solutions to systems, though, in other methods, and we're going to learn those methods in a little bit. So systems of equations, the solution when we graph it is going to be in the intersection of the two lines, which for this system is right here. And so if I'm asked to choose which of the points is the correct solution to the system, I'm going to look for the point of intersection, and then I'm going to write the coordinates. So this is 2, 4, and then I'm going to look in my list and see where 2, 4 is, and here it is right here. It's B. So the solution is B, and it's really because that is the point where the lines intersect. Because the solution to a system of equations is the point that makes both of them true. And a graph of a linear equation is the set of all the points that make it true. And so if we graph two equations, two different lines, the point where they intersect will be a point that makes both of them true, because it's on both lines. So when we're looking at a second example, and we're given this point here, it's just a matter of making sure I know that I go horizontally first and then vertically. So it's -2, -3, so that means it's C, and it's the same reasoning as before. That is the point of intersection of the two lines. So when it comes to finding solutions on graphs, it's just a matter of finding the intersection of the two lines. So what we just saw was that we could solve systems of equations by graphing. And graphing will always work. You would use the same methods to graph as we did in Unit 3, where we'd find 2 points and then insert the line, add the line, and you do that for both equations. The intersection is where the solution is. So we'd look for the intersection, and then that would be our solution. And that is certainly a way of solving a system of equations. However, there are also two algebraic methods, substitution and elimination. And you will always choose which one to use, because they'll both always work. It's just sometimes it might require more work to do one than the other, so it may be more efficient to use one in certain situations than others. And the only real difference in these methods is the first step. And we'll talk about that in a little bit, but that's really the only difference, is the first step. The first step helps us set up the system to solve. So when we look at the two methods, substitution requires at least one of the equations to be in slope-intercept form. That's because you're going to take the expression on one side that's in terms of x and substitute it for y in the other equation, because that equation is set up as y equals, which means I can replace one side of that equation with what's on the other side. And if what's on the other side is just y, I can replace y in the second equation with that expression. We could, if we need to, transform a standard form equation into a slope-intercept equation to use substitution. Usually we prefer not to do that, but you could. Usually when we use substitution, we already have equations, at least one equation, in slope-intercept form. Elimination, both equations have to be in standard form to do elimination, and that's because of the way it's set up. The idea is that we add or subtract the two to get rid of a variable. And we could transform a slope-intercept form equation into a standard form equation if we want. Again, that's going to be more work, but we could do it. Usually when we already have both equations in standard form, that's a good time to use elimination. So when it comes to an overall process of solving systems, the first step is to choose a method. And that means determine which one you're going to do based on your system. If you have at least one equation in slope-intercept form, you should probably substitute. If you have both equations in standard form, you should probably use elimination. Then you do the first step. And again, the first step is the only difference between these two methods. When you substitute, you're replacing y with some other expression in terms of x, which removes y from the equation and creates an equation that has one variable in it. Same thing with elimination. It's just a different process. Sometimes we have to multiply one or both of the equations. Sometimes we don't. And then once we've decided whether we need to multiply or not, then we add or subtract, and the goal is that we get rid of one of the two variables. And it could be either x or y. And we choose that. And if we can just add and do it, great. If we can't just add, we have to do some more, then we do that. So once we've done that, the rest of it is the same. We have one equation with one variable, so we solve for that variable. Once we have that value, we can take that value, plug it into one of the other equations, or one of the equations, and solve for the other variable. So if we have an equation in terms of x, we solve for x, we get the value for x, we plug it into one of the equations, get y. Once we have both values, then we take both of them into the second equation to verify the solution. That shows that both equations have that point as a solution, and therefore it's the solution to the system. And so the fourth step is very important. You can't skip it. So the whole process is do your first step, choose your method, do your first step, then solve for the remaining variable, plug that in to get the second variable, plug both in to verify. So we're going to see some examples of that in just a minute. So when it comes to substitution, our first method of substitution, and the easiest method, is one that's kind of known as the set equal method, and it's when we have both equations in slope-intercept form. When we see that, we have a y equals and then intercept and slope, and that's how both equations are structured. So the goal is to solve for x and y. What we do is we're going to take this expression, because it's equivalent to y based on its equation, and we're going to substitute it for y in this second equation. So our new equation, 22.5 minus 2x equals 30 minus 3.5x. Now I have one equation in one variable, like I did in Unit 2. Now I'm going to solve. In this case, I'm going to add 3.5x to both sides because I think that will keep me positive with the coefficient of x. 22.5 plus 1.5x equals 30. Then I'm going to do my two-step equation solving, so subtract 22.5 from both sides. 1.5x equals 7.5. Then I divide by 1.5 to get x all by itself. And the value I have for x is 5. So now that I have 5 as a value for x, I go back to one of the two equations. I can just choose the first one because it's first. And I'm going to substitute the value I found for x into x in that equation. That way I have another equation now that's only got one variable in it that'll find y. And this is just calculating at this point. I'm just going to do my calculations and get a value. So I've got 12.5 as my y. Now I need to verify, so I'm going to plug the y value in for y and then the x value in for x in the second equation. This will verify. So I use the first equation here, and this is the second equation here. So now I'm going to verify that this is correct. So 30 minus this ends up being 17.5. And then 30 minus 17.5 is 12.5. So we have verified. So our solution is 5, 12.5. And I know that because that's the point that made both of them true. I showed it was true for, after getting x here, I showed it was true for the first one here and true for the second one here. So it's the point that makes both of them true. Also, I can substitute when I have just one of them in slope-intercept form. But that kind of also means that I'm just going to take this expression and it's going to have to go into the standard form equation there. So this will be a slightly different process, but it's still the same, because once I've done this, I've got one equation with one variable. I just do some different things. I got to do a distributive property first. Remember that 4 times a negative 2x is a negative 8x, and 4 times a negative 9 is negative 36. Then I can go ahead and combine these like terms. 5x minus 8x is negative 3x. And now it's a matter of solving a two-step equation. So I had 36, add 36, negative 3x equals 24, divide by negative 3, and x is negative 8. Then I go back and I choose one of the equations. Now, in this situation, it's going to be easier for me to find the value of y using this second equation. And so this is really personal preference. I could substitute x into the first equation and solve for y. I just find it easier when I already have y equals to do that, because then it's only doing calculation. And so I got y equals 7. Now I'm going to go back and substitute both values for x and for y into the equation. And I get 5 times negative 8 is negative 40, plus 4 times 7 is 28, and that is negative 12. So my point, negative 8, 7. And that's because that's the one that made both equations true. So one more thing about solving with substitution. One thing that I could do is I could, to set this up to do an equal, or the set equal method, is I could solve this second equation for y so that it was in slope-intercept form. And that's because I can do the same things I would do to solve, even if I'm not finding a value. So I can add 10x to both sides because that's going to put 10x on the opposite side of y, and that's where I want them if I'm turning one into slope-intercept form. Then I need to get y by itself, so I divide by 5, and then I divide this whole thing by 5. And this is kind of another version of the distributive property. If I'm multiplying or dividing, I have to multiply or divide everything on one side. So if I'm dividing this whole side, I'm dividing these individually. So 25 divided by 5 is 5, and 10 divided by 5 is 2. So then I would go ahead and go back here and substitute and do that whole process. And I'm not going to show that whole process again. I just wanted you to see that I could solve one of these for y in order to do the set equal method. Here, in a situation where I normally would do substitution, elimination, I could take one of them and solve for y. And when I do that, I will end up with one of them be -2 plus 3x. It doesn't really look like a -2. But I could solve one of them, and I could also solve the other one for y as well and do a set equal method. But I just wanted to show you that you can use either method on any system. And these are the three kind of setups we've seen. Both slope-intercept, one slope-intercept, one standard form, and both standard form. And so I can use substitution in any of those. I could also use the set equal or the other version of substitution in either one of those. I just have to do some extra work sometimes to make that happen. And then there's elimination. And elimination is, instead of taking an expression from one and plugging it into the other, we're going to take these two, and one thing we can do with these is we could either add or subtract them to make a new equation. And that new equation, luckily, will have the same solutions if you pair them with either one of these equations and create a new system. That will create a new system that has the same solutions as this one. So when I'm looking at the coefficients of x and y, and I'm looking, do either of them either match or match with different signs? And in this case, we have both of these match. They have the same sign. So that means I'm going to subtract, because if I take -3i minus -3y, that will end up as 0. And then I have to add or subtract the whole thing. So -8x minus -3x is really like adding 3x to -8x, which means that's a -5x. The whole point of doing this was to cancel this, so we've canceled those. And then -21 plus or minus a -21 is again plus +21, which is 0. So that means that when I divide by 5, now that I have a single equation with a single variable, x is 0. Then I can do what I did earlier, substitute 0 in for x. This time I have to do a little bit more, but -8 times 0 is 0. I don't have to rewrite that. Now I just have -3y equals -21 divided by -3, and I get y equal to -7. Or actually +7, sorry. I had a negative divided by a negative. So now that y is equal to 7, now I check in the other equation. -3 times 0 minus 3 times -7, or times +7, equals -21. That's 0. That's 21. So now 0 minus 21 is -21. And I wrote 27 for some reason. So that checks out. So my solution is 0, 7, because it's the point that makes both of them true. So elimination, I can start by checking to see, can I just add or subtract the two equations, and that eliminates a variable. So the same thing here. Can I add them or subtract them to just eliminate a variable? I can by adding, because I have coefficients of x that are the same but different sign. So I'm going to add these two this time. It eliminates 3x, or the x completely. 6y equals 30. And then I just solve. I don't want them divided by y though. Divide by 6, divide by 6, y is 5. Then I go back and I substitute into one of the two equations. And it could be either one, it doesn't matter. So 3x plus 10 equals 28. Now it's a two-step equation. Minus 10, minus 10. 3x equals 18. I'm going to finish it over here though. 3x equals 18. And then divide by 3, divide by 3. X is 6. Now I'm going to check that, and I'm going to make sure that, because I know I found y the first time, I'm making sure I plug in the correct values for the correct variable. So x is 6, y is 5. And now negative 18 plus 20 equals 2. That does equal 2. So my solution is 6, 5, because that's the point that makes both of them true. Now sometimes it's not always that easy. I can't just add or subtract sometimes. I have to do some more work. So when I look at this setup, I notice that these aren't the same and these aren't the same, but these are, the 15 is a multiple of 5. If I multiply 5 by 3, I will get 15. So that's what I'm going to do. I'm going to multiply by 3, but I have to multiply everything in the equation. So that means I would have negative 15x minus 12y equals 3. Then I can rewrite the other equation above it. And now I'm ready to go ahead and add these two. Actually, I'm going to subtract these two, because that will eliminate x. Whole point was to eliminate x. 12 or 5y minus 12y is negative 7y. I'm sorry, minus would be positive 17y. And then 20 minus 3 is 17. And then I would solve for y. And y equals 1, so on. I'm not going to finish this one. I just wanted you to see the different version. Again, it's the first step that matters. The rest of it is the same. When it comes to elimination, we may also choose to multiply both of them by something. So we notice that maybe we choose we want to eliminate y. What we would have to do is multiply this one by 4 and multiply the other one by 5. And that would create a common value for y. In this case, they'll be opposite signs, but that doesn't matter. So I would get negative 60x plus 20y equals 80 for the first equation. And then I would have negative 25x minus 20y equals 5 for the second. Then I can add these two because that will eliminate y, and so on. Eliminate y. 60x plus a negative 25x is negative 85x, and then 80 plus 5 is 85. I divide, I get x equals negative 1. So I would still have to verify that those, if I did this way, I could verify that both of those are solutions to each of those by plugging both values into each equation. Or I can choose one of these methods and solve completely and find the values for x and y using the equations, then verifying in the second equation. And as I said, you can take equations and set them up so that we can solve using elimination even when we don't have two standard form equations. It's just a matter of getting x and y on the same side and setting that up. So in this case, we would simply subtract 8x from both sides, because that would remove x from this side, leaving just negative 25. And if I wrote this in the same form, negative 8x plus y equals negative 25. Now I have an equation that is in standard form. I have the other equation also in standard form. Then I could do my regular elimination process. Do any multiplying if I needed to, and then add to eliminate, and so on. If both of them are in standard or in slope-intercept form, I could still turn them both into standard form. I would take maybe the first one, set it up, and add 2x, add 2x. That would be 2x plus y equals negative 3. And then I could do the second one maybe over here, y equals 10x plus 9. Subtract 10x, subtract 10x. Negative 10x plus y equals 9. And then I could rewrite that maybe over here and start my process of elimination. This one I would just have to subtract, and I would eliminate y, and then I could add these two, or subtract these two, I guess it would be, and find my values. So you can do this to do elimination. It's just more work. You don't have to do it. It's sometimes easier to just use the system as is and do a method that's a little more efficient. So normally when we solve systems of equations, we've gotten a single solution. But that doesn't always happen that way. So here's one example of a solution of a system, and we're going to set up for substitution. We have one in slope-intercept form, so we're going to substitute. So I substitute 7x plus 23 in for y, negative 23, and then I distribute this negative one. It's like a negative 1. It's a negative symbol, but it's like negative 1. So that makes both of those things negative. And then I combine like terms, 7x minus 7x, well that's 0, so I don't have to write it if there's another term there. So there's negative 23 equals negative 23. Well, yeah, that's always true, which tells me that this system is actually, it's the same system. Or it's the same two equations, I should say. These two have the same solutions, so therefore they're the same, basically. Like, so if I graph these two on a graph, and I would see only one line, because it would look like one line. It's really two lines, one on top of the other. They have all the same solution, so it doesn't matter what point I choose. Therefore, they're infinite solutions, because all of the points that work for one will always work in the other. So I'd say that it's infinite solutions. And that's always when I end up with an equation that is true no matter what. So if I end up with 0 equals 0, 15 equals 15, 20 equals 20, whatever, that situation, like this, negative 23 equals negative 23, tells me that there are infinite solutions because these two are actually the same. The other special case is a little bit different, but not too much different. In this case, I'm going to multiply this one by 4 and this one by 3 because I'm setting this up for elimination. So negative 12x plus 12y equals, what is that, 76? 12x minus 12y equals negative 36. So now I'm going to add these because that'll eliminate a variable, but you can kind of see what's going to happen here. Negative 12x plus 12x, that's 0. 12y plus negative 12y, that's also 0. Everything's 0 over here, so I'm going to put a 0. 76 minus 36, that is 40. 0 does not equal 40. That is not a true statement. Therefore, there are no solutions to this. And on a graph, these would be parallel lines. And I would know that on a graph because they would have the same slope but a different intercept. And that's the reality. If they have the same slope and a different intercept, that means that they will never ever meet. And if they will never ever meet, then then there are no solutions to this system. So those are the two special cases when I end up with an obviously right equation, 0 equals 0, number equals number, that is infinite solutions. If I end up with an obviously wrong one, 0 equals 40, 2 equals 5, whatever it is, then it's no solution because there's no points that will work for both of them. Otherwise, if I end up with a solution, I have one solution.